introduce the next speaker, Paul Edelman from, believe it or not, the Department of Mathematics and the Law School at Vanderbilt University. I think he is the only existing example of this. I don't know that very well. Paul had his undergraduate degree from Swarthmore College. I'm going to read a plug Swarthmore. Got his PhD under Richard Stanley at MIT sometime in the early 80s, I believe. 1980. I've known him since just about then. We have a sort of an interesting relationship, is that we both changed fields, more or less swapped them. So now he asks me questions about game theory, and I ask him questions about weak distributed lattices. And anyway, Paul will today tell us exactly what is a combinatorist doing in the law school. Title is The Dancing Bear.
All right, thank you, Lou. Thank you for the invitation. I don't do lots of conferences. This is probably the only one I would come to, because it's a great delight to see old friends from Minnesota and elsewhere. So, as we noted, I'm in the. Can you hear when I speak loudly enough? Yes. Back there.
Yes.
Okay. So, I'm in the law school. I've been in the law school at Vanderbilt now for 14 years. And during that time, I'm sort of talking to lawyers and trying to see what mathematics might be able to tell lawyers something interesting about the law. So in particular, I want to say that. And I might do some, I'm interested in doing some mathematics on the side, but my main goal in going to the law school was to find out about law. Now, a lot of you might think that that's a fool's errand, and a lot of people do. That mostly, mathematicians in a law school is like the dancing bear. So there's this way. I think the British have a version about dogs walking on two legs. What I want to try and convince you today is that this bear can dance. I'll let other people decide how well it dances, but I want to convince you that at least we can do a two-step or two while we're in the law school. If you're training to be a dancing bear, it's important that you don't start out by trying to lead. Okay? You step on people's toes, they get upset. Really, uncomfortable things both for you and your partner will result. And so, one of the things that I learned as I learned to dance was that it helps a lot if you try to follow. And when you try to follow people who think about things a lot differently than you do, and trust me, lawyers do, you actually learn to think about, sometimes there are more interesting mathematical questions that come up doing that than thinking as a mathematician, which I hope to illustrate a little bit. So here are some of the goals for today. I want to show some combinatorial problems that have come up in thinking about law. And I'm going to concentrate on one little corner of the world, and that's about voting power. But I'll say something else about other necks of the woods where this will come up. I want to say something about why, if you're thinking about things from a legal context, you actually you come up with different problems than you might if you were thinking about them purely mathematically. Different things are important. And so you think it now. It's not to say you couldn't have come up with such a problem, but certain problems are natural when thinking about things one way. They're not so natural another way. I want to illustrate that. And then I want to say something about, if you're modeling things in the legal context, and I think this is a little more broadly true in social science, that the modeling is really different than in, say, doing engineering or physics. It's a much different kettle of fish. So, I'm going to talk about voting games. I'll say something else about other examples, but this is a natural place where I think a bear can have some advantages. So I'm going to set things up this way. There are lots of different ways and names for these things. So N is my set. We're going to call them voters, because we're going to think about voting. What we call a simple voting game is just a map from the subsets to 0 or 1. You can think of these as Boolean functions. from the Boolean cube right to 0, 1. We're going to make the value of the empty set 0, and it's going to be monotone. All right? So this setup appears in a bazillion different ways, right? I mean, these are the things that take on value 0 here form a simplicial complex, for instance. These are Boolean functions in another context, monotone Boolean functions with n inputs, which is the way the computer scientists think about them the most. Though it's equivalent to these other gadgets, I'm going to call them voters, and I'm going to call the things that take on the subsets that take on the value 1 is called winning coalitions, and the things that take on value 0 are losing coalitions. And the idea here is that if a subset of voters, that if they cast ballots in favor of something, it will pass. Right? Those are the things that are going to take on value 1, and that's why they're called winning coalitions. They can force the success of a ballot, and if it comes up 0, then the proposition doesn't pass. All right? Particular importance are what are called weighted voting games. Sometimes they're called threshold complexes. Right? There you've got a weight Q. You have assigned weights to each of the voters, and you say something wins if the sum of the weights associated with that subset is bigger than the threshold Q. So it's a standard definition in threshold functions in simplicial complexes and other places. Here we'll just call them weighted voting games. All right, so they're threshold complexes. So here's sort of the key idea that we're going to play with for our purposes. Oh goody, all the fonts came up right. This is a challenge. Okay, so a simple voting game, new here. We're going to take a voter J, and we're going to count the number of times that the value of the subset changes when you add J to a set that doesn't J. So in a voting context, right, 2 times this is the number of times that if J changed its vote, it changes the outcome. It's called being a pivotal voter. Why 2 times? Well, this thing just counts an edge, right? One way to see this is if you're thinking of threshold games, if you've got a threshold Q, it divides this cube, Boolean cube, into 2 pieces. The one containing 0 are the stuff that it loses. The stuff on the other side of that hyperplane are the ones that it wins. And you're looking at the edges that go across in each of the various parallel directions. And we're going to count the vertices on each side. Because if they change their vote, you toggle back and forth, win, lose. That's why there's a 2 here. Doesn't make any difference because it's a scale, but that's what it is. So this is sometimes referred as the sensitivity for the player J. Sometimes called the influence. And we're going to think of it in the voting literature, it's called the voting power of J. It's the ability of J to change the outcome. So we're going to let 2 things compute 2 things. I'll tell you something else. So the first is what's called the Banzhaf measure. What you do is you count up the influence for each. This is a vector. You look at the influence of each voter, divide by 2 to the n minus 1. So this is a probabilistic interpretation here I'll give you in a second. This is what most computer scientists and mathematicians have focused on, measure. I'll tell you why in a second. Actually, I'm going to be more interested in what's called the Banzhaf index, where you normalize it so that the sum is 1. You take these etas here and divide by the sum of the etas. So you're putting, this is now a vector in the standard simplex. All right, so the measure has the stuff with the 2 to the n's, the index is in the simplex. So the Banzhaf measure corresponds to this probabilistic model where every voter has an equal chance of voting aye or nay. All right, or each subset is equally likely to appear. And what the Banzhaf measure then captures is the likelihood that a particular voter will be pivotal. This definition goes back to Penrose in 1947. He wrote a little monograph. It disappeared off the face of the earth, and the only reason anybody even pays attention to it now is for subsequent matters, and they all have to go back and say, well, this was really due to Penrose. Poor Penrose. I mean, you know, but that's life. For us, and you'll see why in a second, the Banzhaf index is more suitable for what I want to do, which is where the law is going to come in. All right, so here's the example. If any of you have taught or had the misfortune of teaching, some sort of math for social science, math for the liberal arts, math for the cerebellum impaired, whatever. You probably had to teach this example of the Treaty of Rome from 1958. So this was the founding of the European Economic Community, mostly about coal back in the day. And there were 6 countries involved: France, Germany, and Italy. Oh, by the way, France beat Nigeria today, 2-0. Big whoop. France, Germany, and Italy. I'd say that about anything. I don't care about that. France, Germany, and Italy. Belgium, the Netherlands, and Luxembourg. And this is the way we denote a weighted voting gauge. So you need 12 votes to pass. That's Q. France, Germany, and Italy, amazingly, each got 4 votes. Belgium and Luxembourg got 2. Belgium and the Netherlands got 2, and Luxembourg got 1 vote. All right, so this is a standard voting game, weighted voting game. So, just as an example here, what are the coalitions for which France is pivotal? Well, France will be pivotal in those coalitions where these are half of them, the ones where France is in it. So FGI, that gives you 12 votes, and that wins. But if France were no longer in that coalition, if France changed its vote, it would just be 8, it fails. So these are half the votes, and the other half would be take those away, and France would be pivotal in the others as well. All right, so there they are. You can go through and check. So the bands-off measure, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm dividing by 32, so I should have doubled this and then divided by 2 to the 6th, but I mean, whatever. Here it is. So these are the bands-off measures. There's the bands-off measures for Belgium and Netherlands. And there's this funky little bit here. I don't know if we have anyone from Luxembourg in the audience, but Luxembourg's power here is 0. Right? Which is to say, it doesn't matter how they vote, the outcome is the same. Now, who exactly arranged that, I'm not sure. Like I said, if there's someone from Luxembourg who could explain, I would appreciate it. I've not seen anything in literature about the negotiation. But this is to illustrate, of course, that voting power is considerably different than voting weight. Right? They're 1/12 of the total. Well, there's 12, and another 5 to 17. Another, yes, 12 and 5 to 17. Right, so they're 1/17 of the weight, but there's 0% of the power. It makes no never mind what they do. All right, so these things have come up when the biggest literature is in the scientific literature is in computer science, where you think about Boolean functions and the input, and you want to know what the sensitivity is to various inputs in these Boolean functions. And so some earlier work, the nicest thing and maybe the most fundamental result is this one due to Jeff Kahn and Gil Kalai and Nadi Leal in '88, where they look at the bands-off measure. So if you use the edge isoperimetric inequality, think about taking the cube in n space and dividing it into 2 pieces and counting the edges that go across. The sum of those edges, sum of the number of edges is basically this band. The 8 is you can count them up using the edge isoperimetric inequality, and you get that the sum of the BMIs is going to be bounded below by n, by 1/n, with the appropriate scaling of the 2 to the n in the denominator. They use some really beautiful harmonic analysis and to compute this square here, some of the squares, the standard deviation, and in fact show that there's always going to be at least one player whose bands-off measure beats the 1/n, beats it by a product of log n. This is a gorgeous piece of work, by the way, and I heartily, there's been a lot since. If you're interested in something like this, there's this beautiful survey by Ryan O'Donnell that you can pull off the web at CMU that does all these things. It's really quite extraordinary. All right. Now the bands-off measure, as you'll see in a second, that's where sort of the fundamental, most of the mathematical results lie in, because it's the natural thing to do. It turns out that these the bands-off measures are essentially Fourier coefficients if you do the right Fourier analysis. All right, so I now we'll switch to the other side of my appointment. So, one of the things I notice is when I talk, I end up talking mathematics to lawyers and law to mathematicians. This is sort of like with Lou, I think we were probably maybe both better off that we switched jobs, so that maybe the fields are better off. I think it's like the stupidest person moving from Tennessee to Arkansas, and the IQs are raised in both places. But anyway, I ended up talking about mathematics with lawyers and law with mathematicians. There are lots of explanations for that, some flattering to me and some not, so I won't go into them. But everybody likes law, and of course everybody thinks they know something about law. And since mathematicians think they know everything about everything, this discussion is very interesting. So let's think about law for a second. I want to start here in 1962, which is well before most people here were born, I suppose. This was before the one person, one vote. So for instance, in New Jersey, a state senator in one district had 35,000 people that he represented, and in a different district had 905,000 people. All right, this is not what you consider, even under gerrymandering, this would look a tad bizarre, right? Minnesota, in the state legislature, there would be one representative for 7,000 in one district and one for 100,000 in another. All right, California, the ratio of the sizes between districts could be as large as close to 300 to 1. All right, this was actually perfectly fine at the time. Now, there are a lot of this was because of, massive industrialization over periods of time, people moving off the farms, coming to the cities, and huge demographic changes over this period of time. And the districts, state legislatures, never agreed to change things. And there are a bunch of cases then in the Supreme Court, starting in '62 with Baker v. Carr. Baker v. Carr, there have been many attempts to get the court to do something. Finally, in Baker v. Carr, the federal courts said, well, you gotta do something here. Reynolds v. Sims is where one person, one vote came into play, which basically said now when you apportion, you have to apportion by population, and the different districts have to be of equal size. This was for state congressional districts. And then finally, 68 was Avery v. Midland. 68, this is actually, pretty recent if you think about it. This one person, one vote requirement ends up going down to local governments, library boards, park districts, the whole works, from top to bottom. A lot of people argue that this is like the single most dislocating decision by the Supreme Court ever. All right? It affected literally every man, woman, and child in the United States in massive ways. And in Baker v. Carr, we already have a little bit of a preview here. We're about to enter the mathematical quagmire to which this court catapults the lower courts. This was Justice Frankfurt. So here's what happened. Every local place is now told, you've got to break up into districts. They have to be of equal size. All right? This is costly. It's also, throws potentially certain people out of jobs. So if you're a local legislator, what do? Well, you try to do something that's not going to be too much of a problem. So here's what you might try. Suppose you have 3 districts, and say this is a county board. I said state here, but it's better to think about it as a county with a bunch of towns in it. And suppose there were 3 towns, each with 4,000 people, 2 towns with 2,000 people, and 1 town with 1,000 people in it. All right? Well, so what you would typically do in this situation is the mayor of each one of these towns would sit on a county board. So some mayors would represent 4,000 people, some mayors would represent 2,000, some would represent 1,000, and the court's saying, So what do? Well, here's what you do. You say, okay, let's give the representative from a 4,000 person district 4 votes. And the one from the 2,000 person gets 2, one from 1 district gets 1. We take 9 votes to pass, we have a weighted voting game, and Bob's your uncle, right? There you go. Right? Does this mean 1 person, 1 vote? Why not? Right? Everybody's representing, the number of votes per person. Sounds good, right? Well, maybe not. All right, so here comes John Banzhaf III. Now, some of you might have heard of Banzhaf or seen the name before. Here he is. He got his Bachelor of Science in Electrical Engineering in 1962, went to law school in 1965. I love this. I pulled this off the web. The one I love the best is he's the father of potty parity, which is to say he's filed a number of suits to make sure that there are not an equal number of restrooms for men and women, but an equal distribution of time spent in restrooms for men and women. See, and you think lawyers can do no good. So the story is with Banzhaf, he was a third-year law student at Columbia when, see, this is 65, and these cases were starting to come down. The last one, Avery Midland, was, but they'd been percolating through, and so people realized this was coming. And so there were certain papers being written about what I just described as a way to do weighted voting to avoid redistricting. And such a paper, this story I'm telling I got from a book by Dan Felsenthal and Moshe Machover on voting power, which is a really nice book, a very nice read. You should buy it if you care. And apparently this paper came to the Columbia Law Review advocating the sort of weighted voting that I just outlined. And the editors at the Law Review, one of the oddities of law reviews is that they're third-year law students deciding what gets published. They, of course, didn't know what to make of this, and they said, well, geez, you know, John Banzhaf, he was a BS in electrical engineering from MIT, maybe he can figure it out. So they gave it to him, and he looked at it and said, well, this can't be right. This can't beat one person, one vote. So he wrote a paper, it's called Weighted Voting Doesn't Work. And what he said was essentially, look, to meet one person, one vote, you got to look at what the voting power is, not just the weight of the vote. The weight of the vote is inadequate to describe what's going on in one person, one vote. And we should look at this Banzhaf index. Now, why the index? The reason you look at the index is you don't care about total power. What you care is the relative power between the people. So whether it's up or down, who cares, right? It's the relative size that matters here. And amazingly, in Iannucci, the Board of Supervisors, this is a New York State case from 1967, this was about the structure of the Board of Supervisors in Washington County, where they did just basically what I described. Each town had a representative on this board, and they tried to do weighted voting and based on the weights. And Banzhaf filed an amicus brief in opposition to this. And the chief judge of the courts, actually agrees with him. Significant standard, as Mr. Banzhaf points out, is not the number or fraction of votes, but rather, quote, his ability by his vote to affect the passage or defeat of a measure. This quote comes directly from Banzhaf's amicus brief. That's pretty cool, right? Now, it turns out, while it seems to be fine in the Washington County, New York, a similar thing was tried in Nassau County, and the judge in Nassau County found weighted voting unconstitutional. So, Nassau County, it's unconstitutional to do this, but if you go to the Washington County website and you look at how they vote on the Washington County Board of Supervisors, you see that the town of Argyle is represented by Robert A. Heinke of Post Box 173 in Argyle, and a simple vote gets 270 votes based on the size of Argyle. And when there are certain measures which require a 2/3 threshold instead of a half, he gets 242. And they computed these numbers, and these numbers are computed so that the Banzhaf index of the various towns correlates with the percentage of the vote, the percentage of the population that that town is in the total count. And every 10 years, they redo this. In Washington County, and in Rockland County, and one other county whose name I can't remember right now in New York. Meanwhile, stones throw away, it's unconstitutional to do this. Another vagary of the American legal system. All right, so, and I'll come back to that in a second, but this sort of starts to raise some design questions, like, who found those numbers? Right? And what did they find they go about doing it? There are a couple of people actually at Ithaca College who did this for a number of years. I don't know if they're doing it now, but so here's some design questions for you. Let's take the standard simplex and pick a number in it. Pick a vector in the standard simplex. Can you find a weighted voting game whose Banzhaf index is close to it? Now, why weighted? Well, you can explain weighted voting to people. If you go to somebody and say, here's a simplicial complex. On the other hand, it does raise the question, is there any voting game? And are these different? Right? Are there vectors that are Banzhaf index of some voting game, but not of a weighted voting game? What does close mean anyway? Now this is a question mathematicians often don't really worry so much about. You'll see why we're not going to worry about much of it either, but it's not for good. And, you know, if you can't get it, how do you find it? Right? If you can get close, whatever close means, well, go find it. Where is it? How did they come up with that table? And how close was that table anyhow? All right, so bad news first. I want to talk a little bit about close. This is something that I think, you know, this is what law does for you, or makes you think about. You know, mostly when you're dealing in mathematics, choose an LP norm, right? I mean, who cares, right? It's squares, absolute values, p, 1 over 2, well, yeah, who cares? It's close. Well, no. So there's this case from 1971 that says that, no, close means this. Well, this is what the metric is. Now, it doesn't take a lot of experience with metrics to know this is not well behaved. Right? This basically sucks. But you ain't got no choice. That's the metric. Now, you might say, well, where did they, what's the matter with these people? Well, it turns out that there's a reason why that's the right metric. And it has to do with political theory and the theory behind what one person, one vote is and what the right to vote is as interpreted by the Supreme Court. So, I will not give you a whole disquisition on the subject. Nevertheless, the right to vote in the United States is not a systemic right. All right? It's not about the overall fairness of a system. If it were, you might think like an LP norm, square root of the sums of the squares, bad things in some things will make up for good things in some place else. But that's not what the Supreme Court says the right to vote is. In the United States, the right to vote is an individual right relative to other people. So if you have a claim of not being appropriately represented, it's because your share of representation is somehow not as good as somebody else's. All right? They're pairwise comparisons. So you have to look at something like the most over one with the largest, more percentage highest power, and take the gap between that and the person with the percentage lowest power. And you try to minimize the gap between the highest and the lowest because that's the basis of the right to vote. Good or ill, that's why you do this. And as a political theory matter, it ain't crazy. Could be wrong, but it ain't crazy. It actually, for what we're going to talk about, I'm not going to deal with this at all because nobody knows anything about doing this. If you do the theory of apportionment, though, which I've written about elsewhere, if whether you use this or something else actually makes a tremendous difference. You get much different apportionments in the United States if you follow this rule than if you follow some other ones. Oh, the other thing is, okay, when you say how close, there are two things. One way is how to measure. The other is, well, what's the threshold going to be? And the court actually has spoken on this. For congressional districts, this thing has to be less than epsilon. Well, okay, so epsilon, but see, epsilon here actually means something. So they threw out a districting in the state of Pennsylvania where there were 9 people different between the biggest district and the smallest district. 9. Now, if that's not the definition of epsilon, I don't know what is. All right? for state representatives, that difference can be 10%, and you're in a safe window. For local districts, it can be as high as 12.7. It will be struck down if it's 14.9.
Does this mean that if a large family moves from one district to the other, they need to do the whole thing?
Just only if they can move wherever they want after they've been counted. All right. So here's some things, though. So how are there vectors you can't ever get close to? Right? What can't you get this way? So this is a theorem that Nova and Alon did and I did a few years ago. It's a little bit technical, but it basically says the following. If you're trying to get a vector where all the power is concentrated in the first k coordinates, all right, so the sum of the last k, it's the length n and the last k minus n coordinates here sum up to less than epsilon. So all the power is concentrated in the first k. Then in fact, that vector has to be really close to something that's identically zero and just has the same power in the first k, which is to say it has to be essentially a Banzhaf index in the lower dimensional face of the simplex. Right? There are only a finite number of these things. There are only a finite number of simplicial complexes. There are only a finite number of these Banzhaf vectors. You know, if you're on the boundary, you've got to be really close to something that's really there. You can't sneak up on things that aren't there in the boundary themselves. So for instance, Kurtz used this idea. So in 2 dimensions, right, either all the power, one person is 1 and the other person is 0, or they're each 50-50. Those are the only possible Banzhaf indexes in 2 dimensions. So if you try to get a vector that's 75, 25, and lots of zeros, you can never get closer than within 1/9 under the outline. So there are vectors that you can't get close to even as you throw in more and more people. So this, in fact, the proof of this has nothing to do with weighted voting games. It's just about simplicial complexes in general, any voting game. Does weighted voting restrict the options? This, I think, is a really interesting question. Right? So you look at the Banzhaf index, is it the same if you restrict yourself to weighted voting games or not? So for practical reasons, right, like I said, you want to restrict yourself to weighted voting games, but you don't know. Are there vectors that you can realize as Banzhaf indices of voting games, but not weighted voting games? And the answer is yes. There's a really nice example by Eric Oz and Svante Linnaeus, who found a collection of these at n equals 5 and sort of an infinite bunch of them, of where the Banzhaf index is not the Banzhaf index of any weighted voting game. It's really beautiful. It's very, very pretty. And it's unfortunately unpublished. So, and Eric is here. So, he's down front. So I will, swarm him, tell him to publish it. It's really pretty. And I think incredibly surprising. To me, it's surprising. So, can you say, is there some sort of purely combinatorial condition? We know combinatorial conditions that describe threshold complexes from arbitrary complexes. Is there some sort of condition on these vectors that would describe the vectors you can't get? Probably not, but I don't know. What can you do in terms of approximation? Well, if n is really big, it turns out, this is another thing that goes back to Penrose. There's some dispute as to how much whether he really proved this or not. But there's a very nice paper that sort of works out the theory by Lindner and McIver that basically says if you have a lot of people, for large n, weighted voting game where the weights are nicely distributed, all these things should be in quotes. This is one of these probabilistic, law of large numbers, sort of nonsense. That if you, that the Banzhaf weights, the Banzhaf indexes, the ratio, is basically going to look like the ratio of the weights. If things are big enough and the weights are well enough distributed. And this is pretty much what you do when you're trying to do one of those big county boards. That seems to be big enough that you can just assign the weights are, in fact, as proportions, going to look like the powers. So if you're trying to build something where you have large N and the weights that you're trying to get aren't too bad, you sort of start with what you think you would start with, and then you can do some hill climbing or some other things to get around it. Small games, you can do some direct enumeration, but not pretty small. You know, what's Eric's, did you do up to 6 or 7? You did 5, you told me. But, you know, beyond 10, you're pretty screwed, all right? And so it's the middle range where things are the hardest to do. That actually turns out to be an important middle range as a practical matter. The practical matter is if, for instance, you want to design a corporate board. And the corporate board, because of the nature of the inputs in terms of debt, capital, and so forth, you are certain desired powers associated with the members of the board. People are willing to pay you money to try and figure that out. All right, let's go back. So it turns out that this analysis in Washington, E. Iannucci makes actually is wrong. It doesn't stop them. They've still been doing it for years. And I'm not sure why no one has challenged it except, well, it's a little bit arcane. But nevertheless, I mean, things seem to work. And I guess people in upstate New York have bigger problems than this. So at any rate, the problem is, of course, the one person, one vote is about the power of the voters, not the power of the representatives. What we've computed with that Banzoff index is the power of the representative on that board to affect the outcome. It doesn't say anything, but that's not what one person, one vote is. One person, one vote is about the individuals who are casting the ballots for their representatives. So if you're going to compute the voting power of an individual casting a vote, there's this two-step process here. First, the voter is the pivotal in the election of his representative, and then that elected representative is pivotal in a vote on whatever representative board they're on. And it turns out that you can take the product of these two things as measures to get the composite game answer. So the Banzoff measure in this composite game is the product of the two Banzoff measures. So for majority rule, among n people, it's assumed n is odd, right? The probability that you're pivotal is the probability that half go vote one way, half vote the other, and you're in the middle, right? And that's this, which looks like, you know, 1 over root n. So the probability in a majority vote that you're going to be pivotal, that you changing your vote changes the outcome, looks like 1 over root n. But if the weights of the representatives are assigned so they're proportional to the size of the district, all right, then an individual, his power to be pivotal in the underlying vote is 1 over root n, and the power of his representative, if it were proportional to the size of the district, which is what Washington v. Iannucci says it is n, and the power of the product, this product means that an individual voter has power that looks like root n, which is to say bigger districts have, voters in bigger districts have more power. Now, you can see this in the Electoral College, because this is what happens in the Electoral College. This was the third paper in a series of papers that Banzoff wrote. This is from 2004 data. This is the electoral vote. So California had 55 electoral votes. They were about 12% of the total U.S. population in 2004. This is a weighted vote here. These are weighted votes, and you needed, you know, whatever, 538 votes here. You needed 269. Under that game, California's Banzoff power was, you know, about, Banzoff index was about 11.4%, which isn't bad from 12%. Right? New York's is about 6.7%. Its Banzoff power is 5.8%. It's not bad. It's not great, but it's not bad. But now if you look, throw in this population of the state, this I've scaled by 2, then the power of an individual voter in selecting that was 10 to the minus 3 times this. And so the product of the powers looks like this. And here what I did is I took the ratio of the power of the power of this state to the smallest power. The smallest power in this case was Montana. So in this voting game for the Electoral College, California ends up, a citizen in California ends up with 3 times the amount of power as a citizen in Montana under this model. All right, so Iannucci is wrong. What you really want is not that the Banzhaf index should be proportional to the population. It should be proportional to the square root of the population. It still doesn't stop. All right, here's a different kind of application. What I'm doing here. A colleague of mine, so I live in Nashville. Oh yeah, good. I live in Nashville. It's a unified city-county government. It's got 40 city metro council representatives on it. 35 of them are districted. Right? The county's divided up into 35 districts. All the districts are more or less the same size. And there are 5 who are elected at large. This is not an uncommon municipal structure. The history of it is rather interesting. Why 5? Well, it turns out when they brought it in, there were 5 power brokers who had to be bought off. Enough said. And so 5 continues to this day. Now, having 40 representatives on a city council is a lot of people in a city council. Or at least some people think so. And the mayor decided he wanted to have a commission to look at the Metro Council charter and think about shrinking the city council. Fine thing to do, but there's a problem. Well, there's many problems, but one problem is, okay, if we shrink it, how do we figure out how many at-large we should have? If we're going to keep it large, what's the right number? If we divide it in half, do we divide the number of at-large in half? More or less? Does it go down like a square root? Does it go down, does it be the same? How should one think about that? And so this nice colleague of mine came knocking on my door and said, I'm stuck trying to figure this out. What should I do? I don't know. Let me think about it. So you start to think about it a little bit. So the question is, how do we decide, is there some optimal number of at-large representatives? Well, let's think about it this way. Maybe not perfect, but let's think about it this way. Suppose we imagine that the large representatives are mostly going to vote the same way. They're all elected from the same polity. It's not an implausible assumption. Obviously, it ain't perfect, but it's not implausible. So what you might be looking at then is essentially a weighted voting game where you have one weight of n minus k and k ones with this n plus 1 over 2 as the weighted voting game. We're going to play this weighted voting game, and we can look at the power. And so n minus k is going to be the number of at-large representatives. We assume that district representatives are all divided equally. Because players in the district vote now actually have 2 votes. They also vote in the at-large contest. And we have to be a little more careful about what we mean by Banzhaf measure, because they're casting 2 votes now, one for their local polity and one for at-large, essentially. But they're still symmetric. So, you know, what are we doing here? Well, we could do this. Let's maximize the sum of the Banzhaf measure. The idea is that this will maximize the chance for each voter to be decisive, because the voters are all symmetric, so maximizing the sum maximizes the power of each. Now, I just point out, when I talked about this to my lawyer friends, they said, really? As a political matter, do you really want to maximize the chance that a voter is going to be pivotal? Will that lead to political instability? Maybe we want to minimize the chance that voters are pivotal. You ever think about that, smart boy? And the answer is, well, this answer, sometimes, the answer is a lot more interesting if you try to maximize. It turns out that if you try to maximize some of the Banzhaf measures, you do it where the number of at-large looks like square root of n. So, in Nashville model, it should be around 6 at-large representatives in the 40, and that's not so bad from 5. And so we shrink the number, increase k, we drop this, and it goes by square root. Now, you know, do I believe that this is the way the world works? No! Okay? But if someone's got to redo the Nashville Charter, and they need some principled position to go to, right, as opposed to just making things up out of whole cloth, right, at least you could do this. It's something. Is it perfect? Nah. What's perfect? Some variations. In the city council case, you have separate votes for a pivotal and at large. And it sort of depends on how you measure pivotal. So when an individual votes in that combined thing, they could be pivotal by their vote in the district, or they could be pivotal by their vote in the at large. Do you count that twice, or do you count that once as being pivotal? All right, I counted it twice in the theorem. You could count it once. The analysis sort of gets to be a real pain in the butt, and I never really pushed it through. It's sort of curious, and it's related to this problem, which is a very interesting one. Suppose we change the rules for electing president in the United States. So what we're going to do, there's a lot of complaint about winner-take-all in electoral votes. There are a number of proposals to try and deal with it. One of them would be to district electors, like we district congressional. So you vote for an elector in your congressional district, and then you cast another ballot for 2 at large corresponding to the Senate. Well, actually, you only cast 1 ballot, but it counts twice. Once in your district and once for the at large. Right? What does that game look like? Well, that's a very difficult game to analyze, actually, and there's no closed form for it. A fellow, Miller at University of Maryland, Baltimore, has done a number of numerical simulations, and it seems close, and my guess is if things are big enough, it looks exactly the same as if you did it separately. You cast 2 ballots, but there's no theorem to that effect. And it would be interesting to know. Banzoff wrote a paper about this, and he actually got it wrong. But, few final words. So, about law at least. Banzoff's analysis was considered, his actual mathematical analysis was considered 2 Supreme Court cases. The earlier ones I talked about were district court cases, or New York State. In Whitcomb v. Chavis, this was a challenging at large representation on the basis of race bias. And Morris v. Board of Estimate was struck down, the Board of Estimate in New York, where the boroughs of New York had a weighted voting scheme. And in both, the Supreme Court shot him down. We don't buy any of this nonsense. It's great to read the footnotes, though. Binomial coefficients, all over the footnotes of the Supreme Court report. So this is sort of the takeaway. So we demonstrate mathematically the theory of voting power does not vary inversely with the size of the district. Do you ever expect to see words like this in the Supreme Court opinion? Increase in proportion to increase population, undue voting power. We do not quarrel with the Platonist mathematics, but we note that the position remains a theoretical one. It knowingly avoids any political or other factors which might affect the actual voting power of the residents. Yeah. But in dissent, into this dissent of Justice Harlan is the following. I've been trying to track down who his law clerk was from this time. So this is Harlan's dissent in Whitcomb. These are the largest numbers that ever appear in the Supreme Court report. So Banzoff model, I remind you, takes a look at the, it assumes that every vote is equally likely, right? It's sort of 50-50. Everybody casts a vote one way, 50-50, right? So he says, so if the electorate changes, if instead of 50-50, right, it's 50.5 in one direction and 49.5, then the voting power changes by a factor of approximately 1 million. Or if you fix 300,000 of the voters, this was in Marion County in Indiana, say 15,000 one way, then the probability of an individual casting a tie-breaking vote is reduced by a factor on the rough order of that. Now my calculations are a little bit different, but on the other hand, I have Mathematica, and this was, whatever, 1970. Harlan was a smart guy, crazy but smart. that it? Yeah. So, a couple final remarks. There are a bunch of areas where mathematics, I think, can do something in the sort of way that I've outlined here. Certainly in voting and elections, we've seen apportionment, I've written some on. There are other areas too where there are places where numbers have to be produced. They just have to be produced. All right, if you're giving damages, somebody's getting some money, you know how to figure out how you're going to write the check. And there are places where those actual numbers, bankruptcy, you got money, you got to divvy it up. All right, there are places, corporations, there's lots of voting in corporations. Tort is about assignment of percentages of damages. There are places where numbers have to be produced. And in those places, I think a dancing bear may have a certain competitive advantage over other less mobile creatures. It is one thing to do mathematics inspired by law, and quite another to do mathematics that will have an impact on them. I hope I've indicated that there are interesting math problems. That's a lot different than finding problems that are interesting and that will actually affect the law. I think there are situations, again here, where it has, but it takes a lot of time and effort and stumbling and listening. In particular, lawyers are incredibly frustrating to work with. Their worldview is entirely different. I'll take on my Margaret Mead and Samoa position here. So, mathematicians, what do you do? The first thing you do is you abstract, right? Throw away all the irrelevant stuff. Let's get down to the nub, right? The first thing a lawyer does is say, every one of these things is different, and here's why. So if you throw one thing away, they'll say, how could you throw that away? Right? You've missed all the subtlety involved with that example. Okay, let's put it back in. Well, and it just drives you crazy. It just drives you crazy. On the other hand, right, what mathematicians often throw away really is different. We mostly don't care, because at the end of the day, we want to prove a nice theorem. And it actually doesn't matter whether we care or not. There are guys in little black robes for whom it might matter, and those are the guys you have to worry about. Not you, not the lawyer you're talking to. And the last thing, which goes to the remark in the paper, the remark of in the Whitcomb thing, is as much as one mathematicians, you come in and you go, yes, here it is. Damn it, I've proven it. No. There's always some reason. There's always some reason that's more important. All right? You can phrase things, you can focus on things, it will never be decisive. It won't. It just won't. And to pretend otherwise is silly. I get calls all the time about people who are going to, let's do redistricting. I've got like half a dozen mathematicians sending me email about, I've got this great idea to do redistricting. Yeah, tell me about it. All right, get in line. Redistricting is a political act. It's judged by political outcomes. It is political, right? Nobody cares about you and your mathematics. Get back on your horse and ride away. So, thank you. Yes.
Yeah. Anyone looking, or have you looked at different parts of a district, or different districts may have different voter participation rates?
Yeah, the Supreme, so, yes. And it's a real problem because the court has adopted some of this power idea, you have to be pivotal, but that means you have to decide, what's the right population to measure. And so you could measure total population, which is what they do now. You could measure voting age population. You could measure registered voter population. right? If you're worried about the likelihood of being pivotal, it's about registered voters more than about population, you might think. And the court has always, they've consistently okayed all voters. There's one state, the state of Hawaii, that gets a pass on this because of the Mammoth naval station on Oahu. Don't get me started, all right? So it's never made a fundamental claim about what is the correct or the only, although everybody just uses population, total population, and there's a political theory reason why you might want to do that. But depending on how you measure these things, you can get vastly different answers. It comes up a lot in the questions of undocumented, two places. One is on undocumented workers, undocumented, can't say citizens because they're not, undocumented peoples, right? If there are a large of them, they're not allowed to vote. Do they count for the purposes of a census? The answer is yes. If you want to be very powerful in the state of Arizona, what do? You go find a federal prison and you bring it to your district. Because federal prisoners are counted as being in the prison, but they're not allowed to vote. So that automatically raises your voting power. And people do that for lots of reasons. It also raises the amount of money you get from the federal government under various and sundry programs. So yeah, it's a real question. The court's been very sort of murky on the subject.
Alan?
Yeah, if I understood Harlan's dissent, the issue is that what we measure in actual elections is that people don't vote randomly, and the standard deviation from...
That was part of his story, yes.
Okay.
That was implicit.
Is there then a theoretical work to talk about replacing the Mansell index with something that hits that better?
Yeah, there are a couple different ways you can go down that route. And the question is, should you? Okay? So here's the argument why you shouldn't. The argument is, if we're trying to design a voting system, one should design the system tabula rasa, right? Because we don't know how people are going to evolve over time and change their votes one way or the other. So we shouldn't embed in the voting system any presumptions about which directions one person should vote or the other. So it would be, in fact, that's the argument for why it would be inappropriate to do what you described, There are other people, often people who lose elections, who argue, no, how can you realistically talk about voting power when, we're 20% Democrats in this district and we always lose, all right? This is a political theory question, and it's hard, but one could work out, they sort of assume different probabilities associated with different coalitions and try and do some things empirically, but you always have that problem does past experiences guarantee future results? And then you have to worry about demographic trends, political trends, all sorts of other things, because you do all this many years before the next election.
One more?
This is sort of a trivial question. In the weighted voting game, Q doesn't always have to be like the half of...
Needn't be.
What if then I rephrase my question to, are you in favor of not the statement, not the...
For the most part, I didn't put the definition in here. Usually you throw in voting games where, what's the name of them? Where if one thing passes, then the complement has to lose. There's another name for this kind of vote. You throw in some other, yes, I mean, generally you put in the fact that you can't have two opposing things win simultaneously.
Okay, we'll have to stop now. The next talk will start in 1 minute.